So welcome back to Efficient Algorithms, COMP526. The last time a new unit, Unit 9, our Christmas lecture, where we'll talk about range minimum queries. I'll tell you what this is in a second. Just to set the scene, it's a little more advanced towards the end than I was comfortable of putting on the exam, so it's just for your enjoyment or for your entertainment. But it also nicely closes one last black box that we left open in Unit 8. And since that was just last week, I hope you still have some fresh memories of that. I put some learning outcomes, but again, these are just for orientation. We'll look at this problem, abbreviated as RMQ, range minimum queries, and the connection it has to things we've discussed in the previous unit. We'll see some solutions for that, and up to this point, I think it would be fine to do it as part of this module. But in isolation, it doesn't add too much interesting opportunities to ask exam questions. And then we'll look at the more sophisticated ways that make the best possible solution of this problem possible. Okay. Let's start with a little bit of introduction and what this problem is about. So first of all, just the definition. What is the range minimum query problem? It will at first sound like a very simple and slightly strange problem. Why would you care about this? But we'll come back to that in a minute. So the input is just an array of numbers or arbitrary objects. Static here means it's not changing over time. That's to simplify the problem, and it will be interesting in that variant for us already. So you have n numbers, and you can pre-process that array of numbers up front, and you can build some data structures, do whatever you want. And then later, I'll ask you queries, which will always be a contiguous range, so some start and end indices. And you have to tell me where's the minimum in that range. So in this case, if I ask for the range minimum query that starts at index 17 as index 7 and ends at 15, that's the range. So if you look at those numbers, 2 is the minimum. So I return that position. Two nitpicks about this. I'm not asking for the value of the minimum. I'm asking for the position. So you're returning an index, not a number, a value here. So you would return 10. And if there's ties, then we take the leftmost of those occurrences. Somewhat arbitrary, but that's the conventional way to solve ties here. So far, so good? Let's see. So just a simple example query to test that we're all talking about the same problem. So what you should send back as an answer is just one number. Add 66 on the attendance code, so maybe we can get a few more here too. Let's wait until 40, and then, okay, there we are. Now here's the results. Again, what you can't see is 9 people are behind the 1. And, well, a few other answers. Okay, so let me go through this. I want to draw this the same way. The range, first of all, that we're given, it starts at index 1 and ends with index 6. So the range we're looking at is this. That's the part of the array that we're focusing on, and only what's inside of this range matters. Now we're looking for the minimum, and the smallest number in that range is 4, which occurs twice, here and here. And the actual answer that we return is 1, because we're supposed to return the leftmost index of that minimum. And that's here. Okay? That's what this is about. Now you may wonder why that's at all relevant or even connected to what we've done last time, but we'll come to that. A few more comments on the definition. First of all, notice that everything is comparison based. I'm asking for a minimum, so all I need to be able to do is compare two elements, two objects, and tell which one is smaller. So I defined it in terms of numbers because we'll use it for that, and it's kind of without loss of generality. But really it's comparison based, so it could be arbitrary objects. And then we have, unlike in some other problems, we have two types of running times that we're simultaneously trying to keep in check. One is the pre-processing time. That's the time you spend on the array before any query comes, and then the time per query. And you can maybe imagine that there will be some trade-off between the two. So what we want to keep both in our solutions and be able to talk about both. So I'll use this angle bracket notation to say the two running times are such and such. And the first one is pre-processing, second one is query. Okay? So without really knowing or without thinking deeply about this, maybe you want to give me your best guess of what could be achievable. And I mean, if you've, sorry, no. If you look forward in the slides, of course, you can find the answer, but the goal would be to get your gut feeling instead. So your answer should be of this form with two running times. So for example, in angle brackets 1, 1 would be you spend constant time on the pre-processing and constant time on the queries. I mean, spoiler alert, that's not going to be possible. That's the kind of format that you're aiming for. Yeah, some good answers. Okay, let me show you. Most people seem done. Okay, you broke the algorithm for doing these wordles. Word clouds. The middle one, big O of n for both, might be what we could read it as. Well, I don't want to give much away. We'll see. Okay, I'll just leave it open.